Hello everyone and welcome to Chapter 14, Kinetics of a Particle, Work and Energy. This module discusses power and efficiency. It is important to note that this module will introduce power and efficiency concepts that can be used in problems while you solve them using either Newton's second law or the principle of work and energy. So both of them can be used, either Chapter 13 or Chapter 14 following Hibbeler's book for dynamics. So objectives is first to understand what do we mean by power and efficiency from dynamics point of view. And then we want to utilize, as I mentioned, theories of kinetics and kinematics, whether using Newton's second law or using principle of work and energy, in addition to rope and pulley systems, anything you've seen in kinematics, to evaluate the power and efficiency of particle. Okay, power is defined as the amount of work performed per unit time. Therefore, if a machine or an engine performs a certain task, then the amount of work that is being done, which we're going to call du, within a given interval time dt, is the power generated, and it can be calculated as basically P equals to du dt. This is the definition of power. Now keep in mind, since the work can be expressed in terms of F and dr, we know from previous modules that work equals to F dot R in vector format. Okay. Therefore, if I have du, then it's going to be F dot dr, and this is what we have in here. So P equals F dot dr over dt. Now what is dr dt? This is basically the velocity. So power equals F dot V, force times velocity. Okay, now similar to work, since the definition is based on work coming from work, force and velocity should be on the same direction. So this is the vector format. When you take it to the scalar notation, since power is a scalar quantity, you have to take cosine the angle between them to make sure that the velocity and the force are acting on the same direction. Now, it's important to note, following the units notation, force will give you Newton, velocity will give you meters per second. So 1 Newton meter per second can be written as 1 joules per second. Newton meter is joules, or joules per second can be written as 1 watt. And here's the conversion. 1 horsepower equals 550 feet-pound per second if you are using British unit systems, and it's equals to 746 watts if you are using SI units. So, final thing that we need to define before we go into solving problems is efficiency. The mechanical efficiency of a machine is the ratio of the useful power produced, so the output, which is the power or the energy that is coming as an output of your machine, to the power supplied to the machine, the input. So for example, this could be electricity. When you plug it in, this is input power. And how much power are you expecting in your output? So it could be either power output over power input, or could be written as energy output over energy input. Keep in mind that theoretically the maximum value is 1, but usually due to heat losses, friction, and other sources of losses, the output is usually less than the input. So 1 is the maximum, and you get usually a value between 0 and 1. So let's start with the first problem. A 50-pound load B is hoisted by the pulley system and motor M. Hoisted means being pulled upward. The motor has an efficiency of 0.76 and exerts a constant force of 30 pounds. So I already have the weight of load B, I have the efficiency of the motor, and I have a constant force that is applied of 30 pounds on the cable. Neglect the mass of the pulleys and the cable. Find the power supplied to the motor. When we say supplied, this means input, being given. So the power supplied to the motor when the load has been hoisted 10 feet. When it moves upward 10 feet. So initial position it was on the ground, final position moved upward 10 feet. The block started from rest. Okay, now look at the equation that we defined here. Efficiency was given, power input was asked to be found. So basically I need power output. Power output is basically force times velocity. Force was given, so I need to find the velocity. That's what I need to solve in this problem. So first of all, I need to relate the cable and block velocities, since I need to find the velocity. Then draw free body diagram and apply either equations of motion or principle of work and energy. And finally, calculate the power supplied to the motor, by the motor and to the motor, so that I can find the final value. So let's start with the kinematics. For the motor, this is the first constant or fixed datum that I have. Therefore, Sm will be defined to positive to the left. And for block B, this is my fixed datum, and Sp is positive downward. Keep in mind that this part is constant, does not change, so it's not part of the rope. I do not consider it. And one other thing that students usually have confusion or do mistakes when they deal with motors is that Sm is defined. Usually, if you have a motor, define your S for that motor by just using a random point on that cable. In this case, use any point like this and define Sm to that point. So now, writing the equation, I'm going to have Sm plus 2Sb should equal to L, the length of the cable. Differentiate this to get the velocity. So Vm plus 2Vb should equal to 0. Therefore, I have a relation that Vm should equal to minus 2Vb. Okay? So that's it. Now, let's go to the problem again. Let's draw the free body diagram first. So I have block B. I have two tension upward, and I have the weight of block B downward. Okay? Now, So first of all, the velocity of the block can be obtained by applying principle of work and energy to the block. Since I have only one mass, then I do not need to write any summation. So I have T1 plus summation of work from 1 to 2 should equal to T2. Start with T1, I have half mb, velocity of B at position 1 square, then plus I have two tension, I have 2T multiplied by delta SB, and then I have, since the block is moving upward and the tension is upward, therefore it's a positive work, so it is 2T multiplied by SB. And then minus the block, so the weight of the block, WB times delta SB. This should equal to half MB VB2 square. Now, since the problem mentions that the block starting from rest, then initial kinetic energy is 0. Now, plug in the numbers for the rest. I have 2, T equals to 30, the tension in the cable, and SB is 10. So it is moving upward by amount of 10, minus the weight of the block is given to us as 50 pounds, so minus 50 multiplied by also 10, and it is downward because it's negative because the weight is downward and the block is moving upward, so it's negative work. This should equal to half. The mass is not given, but I have the weight, which is 50, and to make it converted to mass you have to divide by gravity, which in British system units is 32.2. This multiplied by VB2 square. Okay, now solving this equation gives you that VB should equal to approximately 11.35 feet per second. Okay, so I have the velocity now. Now, since the velocity is upward, it is a negative velocity in terms of the kinematic equation coordinates, meaning, go back to this equation. Where did we define SB? SB was defined downward, and in previous modules I mentioned that this, when you start with kinematics, this is what defines your positive and negative. So SP is moving downward, so not moving, but SP is defined from the datum to the block, so it was directed downward, so downward is your positive. Therefore, my velocity is 11 feet per second upward, so this is a negative velocity. So now, I want to relate the velocity of the motor to the block. So what I do, we have the relation, remember that Vm equals to minus 2 Vb. This should equal to minus 2 times. Now, if you put 11.35, it's wrong because it is negative in that equation. In this equation, we are defining Vm positive to the left, Vb positive downward. So in this case, I have to make sure that I write this as minus 11.35, which will give me a positive number, 22.7 feet per second. Okay. Now keep in mind that you can always check to make sure that you have no mistakes. Basically, look at the direction. So Vm was positive, and we already defined Sm as positive to the left, which makes sense. If block B moves upward, you want the point on the cable to move to the left. Okay. Finally, now the power supplied by the motor is basically the product of the force applied to the motor and the velocity of the cable, which we just found. Therefore, output power should equal to the force times the velocity, and they are already in the same direction. So it will be 30, the force in the cable, multiplied by the velocity that we just found, so 22.7, and this should give you 681 foot-pound per second, or pound-foot per second, doesn't matter. Okay. Now, the power supplied to the motor is determined using the motor's efficiency and the basic efficiency equation that we discussed. So, remember that efficiency equals to, let me fix this one. So, efficiency is basically power output over power input. Therefore, in this case, power input should equal to power output over efficiency. This should equal to 681 over 0.76, and this will give you an input power of 896 foot-pound per second. Finally, just to play with the conversion, if I want to convert it to horsepower, or if it was required of you to convert it to horsepowers, then the conversion rate, we've seen it before, so Pi will equal to whatever value that you have, which in this case 896 divided by 550, and this will give you 1.63 horsepower. Okay. So as you can see, this part of the slide. This slide is the only part of the of this module. Previously, I'm just solving a problem using principle of work and energy. I have another example that we're going to solve it also using Newton's law in this case, just to show you that you can use both in these problems. The dumbwaiter D and its load have a combined weight of 600 pounds. While the counterweight C weighs 800 pounds. Determine the power delivered by the electric motor M when you have two cases. When the dumbwaiter D is moving up at a constant speed of 8 feet per second, constant meaning there is no acceleration, and part B when it has an instantaneous velocity of 8 feet per second but an acceleration of 2.5 feet per second square directed upward. So we'll solve part A first. But before we do that, let's do the free body diagram of the two blocks, because I'm going to use it for both problems, for both parts, A and B. So let's start now. Start with C. Okay, so this is block C. I have two tensions of the cable. So I'm going to have 2 of these. So I'm going to say 2t. Okay, and I have the weight downward, which was 500 pounds. Okay, and I'm going to have, of course, the inertia downward. I have MCAC. Okay, now for block D, I can do the same. For block D, I have now 2 different tensions. I have one which is the same one with C, and I have another cable in this case. So I have 2 different forces. So I will have one of them as T, I'll call it, and the other one I'm just going to call it F to differentiate between the 2. So I have one of them called T and the other one is called F. And I also have the weight, which is 600 pounds. Okay, and I also have the acceleration, which was given to me in part 2, so I'm going to use it eventually, which is MDAD. And I used C here downward because if D is moving upward, then C obviously will move downward. Okay, so now I have my free body diagram that I'm going to use for both. So let's start with part A. Part A says you have no acceleration. Okay, remember, you have velocity of 8 feet per second and you have no acceleration. So for this part, I'm going to start with equations of motion for block C first. So upward, let's say, is positive. Summation of Fy should equal to 0. Okay. It is important to note that both accelerations are 0 in this case. So what does this give me? It gives me that 2t, since upward is positive, minus 800, okay, should equal to 0. You can see here. So actually this is 800, sorry, not 500. Let me just check. It is 800, yes. Okay, so 2t minus 800 equals to 0. This will solve t for me. So I get t equals 400 pounds. Okay, now we go to, this is for C, by the way. Now for D, I have upward is positive as well. Summation of Fy should equal to 0. And I have F plus T minus the weight, which is 600, should equal to 0. This gives me that F should equal to 200. Okay. Now, back to the problem. What is required is to determine the power delivered by the electric motor. So if I have the force now, remember that this part of the segment is the one that is going to the motor. So this is my F. So I already have F. I need to find the velocity. Just if I multiply these two, velocity was already given that the dumbwaiter D is moving up at a constant speed of 8 feet per second. So this is moving upward. That means this part of the cable and this one, both are moving with the same speed. So it is 8 feet per second. If you follow it, it's entering here with 8 feet per second, the same thing. So finally, I will write that F times Vd, which will equal to 200 multiplied by 8, which was given. So this will give me 1600 or 1600, and the unit is feet pound per second. And this is your power that is required, that is fed into the motor. And if you want to convert it to horsepower, we did this before, so it will be equal to, so the power will equal to 1600 divided by 550. This will equal to 2.91 horsepower. Okay. Now, the second part of the problem says find the power delivered by the electric motor. Okay, if the dumbwaiter has an instantaneous velocity of 8, similar to the previous problem, but has an acceleration of 2.5 feet per second square. So in this case, from the rope and pulley system, I know that if you want to do it somewhere in here, I know that if you look at the problem, for block C, I can relate C and D because I have acceleration of D. I need to find the acceleration of C. So when you look at this rope and pulley system, I have two segments for SC. So this is my datum. Here downward is my direction for SC and also my direction for SD. Okay, so this is SD and these two are SC in this case. Okay, so what I have is, in this case, 2 SC plus SD should equal to L. This gives me 2 VC plus VD equals 0. This gives me 2 AC plus AD equals 0. Now AD is given as upward, and I know from here that AC should equal to minus half of AD. So AC should equal to minus 1 over 2 multiplied by, remember, AD is moving upward, and here the datum is defined positive downward. So AD will be given as a negative. So it's minus 2.5. Again, SD is defined as downward. So downward is positive. Whereas the problem says AD is moving upward. So it's negative. Okay. So I'm going to say this is minus half multiplied by minus, what was the value? 2.5. So minus 2.5. This gives me AC equals to 1.25 feet second square. So AC is positive, means AC goes down. If D moves up, C moves down, and this is clear. So we go now into the equations of motion. For C, again, upward is positive. I have summation of Fy should equal to MCAC. So this will give me 2T minus 800, the weight, should equal to now AC is moving downward, so it will be negative in this case based on this definition, because I have now upward as positive. So it will be minus, and you have the weight, which is 800. Don't forget to divide by the gravity, 32.2, multiplied by AC, which is 1.25. This gives me that T ends up being 384.5 pound. Okay. Same thing I can do for block D. Upward is positive. Summation of forces in Y should equal to MDAD. Okay. So what do I have here? I have F plus T minus the weight, which is 600. Now AD is moving upward, so it should be positive based on this notation, sign notation that I decided to use. So it's gonna be, the mass is 600, again divided by the gravity, 32.2, divided by AD, which is given in the problem, 2.5. Since T is known from the previous equation, F can be computed to be equal to 262. So it's going to be 262.1 pound. And then the power will equal to force times VD. So this should equal to 262.1 multiplied by VD, which was given in the problem as 8. and this should equal to 2097. Again, write the units as always, pound, feet, or feet-pound per second. If you want to convert it to horsepower, it will equal to 2097 divided by 550. This should give you approximately 3.81 horsepower. And that's it. So the important thing to notice in this module or in this section or in this topic, that these problems with power and energy, they can be solved using Newton's second law or by using work and energy equations. The point is, once you find the velocity, you just have to plug it into the power equations, and if you are asked to relate input and output, then you have to include efficiency into your calculations. With this, I conclude this module. I hope that it was useful to you, and I wish you the best of luck with your studies. Thank you.